So now that we have this context of the decoder only models, we will see the first decoder only model, which is a generative pre-trained transformer, is also popularly known as GPT, and it has of course a family of models, now the latest one being GPT-4, but we look at the first paper which came out in the series, which is the original GPT model, which would be much smaller than the current GPT models which are out. So let's look at what it looks like. So we saw what one block of the decoder only model looks like, right? We just saw one block there. Now I could just stack up n such blocks, okay? So I'm going to stack up n such blocks, and we now know the game, right? So the way it works is that you give it an input, it computes this representation, it computes a refined representation for each of the inputs, right? And it continues this till the end, and at the end it will predict a probability distribution, yes? Right? So it's predicting the new representation at every layer, and at the end it will use that to predict a probability distribution, and that's exactly what we want. Does that make sense? Right? And what we want at training time, that's what we will see now. So let me just make sure that all the notation is understood. It's actually very straightforward, but the input layer, which is the H0 layer, okay, it has a sequence of length t, right? And each word is represented by an embedding of size d model, right? So it could be 128, 64. We'll see what it was for GPT, but it could be any 64, 128, any of the numbers that you want to choose, right? And so that is the input. And remember that the whole computation is happening in parallel while we have this triangular mask applied, so that at every stage you only see the previous inputs and nothing which comes afterwards, right? So you are at one go passing the entire input sequence, which is known to you during training, to the model, but you know that when you are computing this guy, it has not seen anything which comes after it. Is that clear? Right? That the masking has taken care of. So now at the end you are simultaneously predicting all these probabilities, and your job is to maximize each of these for the correct word. Right? So probability of I should be maximum here, am should be maximum here, going should be maximum here, home should be maximum here, and so on. Right? So all of these probabilities you need to maximize, okay? And that at every level you are computing a new hidden representation, which is shown by this. So it's the representation coming out from the Lth transformer block, which takes the input from the L-1th transformer block. The first transformer block always takes input from H0, which is just your raw input, the word embeddings, right? And then at the final layer, the nth layer, you will apply the softmax. Whatever the nth layer outputs, you will pass it through a linear layer and then apply softmax on top of that, and that is how you will get the probability distribution, correct? Okay. So all of this is known, but it's worthwhile to emphasize it in the context of the decoder only model. Fine. So now for, as I said, for each of these guys, you want to make sure that the probability is maximized for the correct output. That's why you have t probabilities here, log probabilities here, and you want to maximize each of them, and the way you encode that as a function is just maximize the sum of those, right? Is that okay, everyone? Right? Okay, so that's how it is, and remember that the attention mask has been applied here. That's why you are able to take the entire paragraph as an input, and at every time step you are sure that only the correct words have been seen, or whatever it is allowed to see has been seen, nothing else has been seen because of this triangular mask that you have used, okay, attention mask. So now that the model is clear, we will do a few things now. We know the basic architecture of the model, which is a decoder only model. So we will first talk about what was the data that it was trained on, and I should warn you that it's very, very small as compared to what modern GPTs or other LLMs are trained on, but that's where we started. So we'll talk about the data used for training GPT, and then we'll also talk about the architecture in terms of what was the dimensions, how many attention heads and so on, and try to compute the total number of parameters that are there in the GPT model, okay. So this uses what is known as the book corpus. It contains some 7,000 unique books, 74 million sentences, and approximately 1 billion words, right, which is, as I said, very small as compared to what modern LLMs are trained on. Also it uses long range contiguous text. That means the sequence length t, as we will see later on, was 512, and these 512 tokens were contiguous because it has books. So it just takes like 512 continuous tokens from a book, and what that means is that it does not really shuffle the sentences, right. So it is contiguous text. So the entire 512 context is one contiguous text which it takes together and feeds to the transformer and tries to predict each of those 512 tokens while respecting the boundaries. That means it does not look at any of the future tokens with the mask, right. And it uses byte pair encoding. So this tokenizer is something that we have not looked at yet. We will look at it when we study the BERT model. We look at what kinds of tokenizers exist. But you could just think of it as a way of tokenizing the input sentence. So if I am saying I am going home today, then a simple tokenizer is that wherever you see a space, you take that as a token, right. But you could do something more interesting, like you could think of frequent suffixes like ing as separate tokens themselves. So then you would split this as I am going home today, right. So that would become 6 tokens, right. So we will see what a tokenizer does, but for now you can just think of it as that wherever you see a space, that's a new token. So when I say 512 tokens, in our layman terms, we just mean that 512 words were passed to the model, but we will refine this understanding as we go along. And the vocabulary size was 40,000. What does that mean? That when I said it's predicting a distribution over the vocabulary, you should know how many unique items exist in the vocabulary, right. So it's just like predicting a distribution over the color of a ball. This our classic example of is what's the probability of it being a red ball, white ball, green ball. So you need to know how many colors are there, right, and then you will predict a probability for each of those colors. Similarly, you could think of the token being a random variable which can take 40,478 values. Each of these is a unique word in the English vocabulary, right. And the embedding size was 768. So the word embedding that you pass as input was 768 dimensional. And so we have some details here. We'll look at few more details about the model. So it contains 12 decoder layers, right. So there were 12 transformer blocks, one after the other. Its context size was 512. That means this capital T that we have been talking about, the sequence length, was 512. Okay, that means it can see 512 inputs at one go, right. Attention heads were 12. That means every layer had 12 attention heads. In our initial discussions, we had seen 8 attention heads, 2 attention heads. So it had 12 of those. The feed forward hidden layer had size is 768 cross 4. Yeah, so 768 is the model size, right, which was the input embedding size. So every layer, right, is producing a 768 dimensional output. Okay. So even the attention head inside produces a 768 dimensional output. Then you have a feed forward network which makes it 3072 and then again shrinks it back to 768, right. So that's what this feed forward hidden layer size was, 3072. Does that make sense? It just says that it was 4 times the model size, right. So this you chose to do a 4 times expansion and then again brought it back to 768. So this figure, right. So this is your FFN, which takes the 768 dimensional input, which is the representation computed by the 12 heads, right. So this is actually 64 into 12. Each head produces a 64 dimensional output. Then you concatenate it, so you get a 768 dimensional output, which matches whatever your input dimension was, right. That's what we saw on the previous slide, that D model was 768. So each of these guys everywhere would be 768. In between, through the feed forward neural network layer, you do this transformation of 768 becoming 3078 and then again shrinking to 768, right. So the hidden layer of the feed forward network is of size 3072. It's not you need to do this. This is yet another transformation you are doing, and a lot of this is like empirical in terms of hyperparameter, right. You could try no one could argue that if you had done 2048 what would happen. It's not an argument to be made. It's just some choice that they made and we're just telling you what the choice is, right. There is no clear argument for why it should be 3078, not 1024, why not 204. Yeah, it's part of the empirical evidence that they have, right. Okay, and they used GELU as the activation function. Now you'll see where does the activation function come up, right, because In the attention heads, there is no activation function, you just have the softmax to compute the attentions. So where does the activation function come? The activation function comes in the feed-forward network. So we'll see where exactly it comes. And they use dropout, layer normalization and residual connections, which helped in faster conversions during training, right. So where each of these was put is what we'll see next, right. So this is what a sample data looks like. So this is actually 512 tokens. The highlighted part that you see there, this is 512 tokens, where I've treated every token as just space separated, right. So actually tokens are more than that because we use byte pair encoding. But for now, as I said, for our shallow understanding, let's think of anything separated by space as a token, right. So this is the 512 sized input that I'm giving it. So I give this entire thing to the transformer, and at the output, I expect it to predict the probability of the corresponding word. Does that make sense, right? So let's see how that happens. So you have the first transformer block and go at the Bell Labs Hamming. So this is the actual paragraph. This is the 18th token research. This is the 351st token, and you continue this till you get to the 512th token or 511 if you're zero numbering. So that's the last token in the 512 sized sequence. Okay. So this entire thing is going to get fed to the transformer block. When I say this entire thing is going to fed, what I mean is that for each of these words, you will look up the word embedding and feed the word embedding to the transformer block, correct? Right. So that's the input to the network. So this input would be T cross D model, right, which was 768, right. T cross D model is what I will write. Okay, so each of this is D model size, right. Each of these embeddings is of size D model, right, and you have T such embeddings because your sequence length is capital T. So your input size is T cross D model. Does that make sense? That means at every layer you will be producing a T cross D model sized output till the last layer, and at the last layer you will then convert it to softmax. So you will be predicting capital T probability distributions. Does that make sense, everyone? It's masked. Yes, because it's masked, we are able to do this in parallel, right? Because we are sure that at every stage I will not look at anything which is corrupted, right? So that's why I am able to do this in parallel. This entire input is flowing through the network in parallel. All the probabilities are getting computed in parallel because I have masked the input. That's the whole point of masking, right? So this is what one training batch looks like, right? I have a batch of say 512 tokens, okay. See, that's not really a batch. This is one training example of sequence length 512. I could have a batch on top of this, right? So I could give 64 such sequences in parallel, right? But for now, let's consider that our batch size is 1. That means I have one sequence of 512 tokens, right? And this entire thing is traveling through the network. All the computations are happening in parallel with the mask applied, and then I finally compute the probabilities at the end, okay? So let's look at the entire thing. So this is my 512 tokens. They will go to this first transformer blocks masked multi-head masked attention. Right? So what does that mean? And then they will go to the feed forward network. So this is what the multi-head masked attention looks like, right? So this is the first head, right? This is the 12th head, okay, right? So the first head will take all these 512 tokens. It will generate the QKV vectors, do this entire operation, and again give me 512 vectors. Does that make sense? Right? And what would be the size of each of those vectors? It is D model divided by the number of heads that I have, which is 12, right? Which in this case would be 64. Okay. So each of these heads is producing a 64 dimensional vector, and then I am going to concatenate them to get back my 768 dimensional vector. Does that make sense? No, they are all taking the same input, right? So there are 512 input embeddings passed here. For each of these, you will compute the Q vector, the K vector, the V vector, right? Then using our standard attention equation, which is this block, you will use the QKV to generate a new 64 dimensional embedding for each of these guys, right? That is what the first head will do. In parallel, the second head will also do that with its own WK, WQ, WQ vector. All the 12 heads will do this in parallel. They will generate this 64 dimensional refined representation for the input, which is mindful of the other inputs by paying attention and appropriate masking, right? So it has generated those 12 64-dimensional vectors for each of the 512 tokens, right. So, you have 512 tokens, for each of them a 64-dimensional embedding is being generated by each of the 12 heads. So, this is 768 and that is what is getting concatenated here. So, then finally, you will get 512 such concatenated vectors of size 768. Does that make sense? Yes. So, you have 512 inputs. So, always have this mind view of transformers, right. Number of inputs same as number of outputs at every layer. And to simplify things further, we keep D model as a constant throughout the network. That is why we call it D model. So, whatever is your input embedding size is the same as the output at every layer, right. So, that number does not change. It is not that we cannot change it, it is just that every transformer architecture has that number as a constant. Does that make sense, right. So, we had a 512 cross 768 input, it went through this masked attention and gave us a 512 cross 768 output. Then each of those 768 guys went through this linear transformation. This is not the feed forward network, this is the linear transformation within the masked multi-head attention, right. This was that WO vector that we had, right. And then we again get a 512 cross 768 embeddings, right. For each of the 512 guys we get 768 embeddings, 768 dimensional embeddings. Does that make sense? Yes, no? Any questions on this? These are all different attention heads, each having their own WQ, WK, WV parameters. Yes. One layer working parallelly. Yes, yes, right. Okay, so this is one layer working in parallel, 12 attention heads giving you the output. This is still the multi-head attention only, we still have to deal with the feed forward network, right. So, after you have paid attention to everyone, you have got 512 refined representations for the 512 input tokens, each being of size 768, okay. Now, after that, let us see what happens. After that, you have the layer normalization and the residual connection. Remember that? We had this layer normalization in transformers, right, and then you have the residual connection which ensures that even if you have a very deep neural network, the gradients still have a way to flow back, which is the same as what we had in the residual networks, okay. Okay, they also use dropout here, right. So, they had said that they use dropout, layer normalization and residual connections. So, I am just showing you the positions of where they use the dropout and where they use the layer nominal and the residual connection, okay. This residual connection of course comes back from the input embeddings, right. So, what is happening here is that you started off with an X, right, you computed some H's for that. You started off with these X's, right. Why are you all lost? Are you lost? Did I go slowly or something? No, you are all okay, right. And this is H. So, X was 512 tokens into 768 dimensions. H was also 512 into 768 dimensions, right. And then what does residual connection means? You are computing H prime, which is X plus H, because you do not want to forget the original X, you just want to make sure that the gradients flow through that channel also, which skips the entire transformer block and propagates the gradients back to X, right. That is the whole skip connection idea, okay. So, that is what is happening in the gory details of just the mask attention. Now, we have got this H prime, which is again 512 representations of size 768 each. This has to go through a feed forward neural network. So, let us see what happens there. So, now this goes through a feed forward neural network. Remember, there are 5, I can't, I will repeat it as many times as I need to. There are 512 of these arrows, right, one corresponding to every token. I am looking at one of those guys now and telling you what happens in the feed forward neural network, right. So, that goes through, this is the input now to the feed forward neural network, which was 512 dimensional. It maps it to, what was that, 3072, and then again maps it back to 512, so that your final output coming out is again, sorry, the input was 768, maps to 3072 and again comes out at 768. This is for one of the guys. The same process gets repeated for all the 512 guys. So, you have 512 cross 768 output. Is that okay? Right? Okay. And and this is the point where you use the GALU activation function, right. So, the hidden layer has the GALU activation function. So far, nowhere else we have used any activation function, right? So the feed forward hidden layer has the GALU activation function. Then after the feed forwards output, you again apply dropout, you apply layer normalization, and you again have the residual connection. This residual connection coming from here. This was the input to the block, so always the input gets added back to the output. Clear? Okay. So this is how the whole network looks like. Oh, sorry, one block of the network looks like. So we have seen that in gory details. So just want to take a couple of minutes again to repeat what is happening, right? So you are taking a very large piece of contiguous text, which is 512 tokens, feeding it to the transformer layer, right? And at every layer you are again producing 512 outputs till the last layer. And at the last layer you are applying softmax to convert these into 512 probabilities. What are these probabilities? P of x1, x2 given x1, x3 given x1 comma x2, x512 given all of the others, right? So those are the probability distributions that you are predicting. All of this is happening in parallel, and the mask is ensuring that you don't see anything which you are not allowed to see. Okay, and these are 12 such blocks which are there. Okay, so now let's count the number of parameters that are there in the network. So the embedding is V cross embedding dimension. So we said embedding dimension is 768, which is the same as D model, and there were 40,000 words in the vocabulary, 40,478. So this multiplication gives you some 31 million parameters. Okay, these I of course not delve onto the answers here. I'll just say, okay, this is 31 million, and you just take my word for that. Then you have the position embeddings. How many position embeddings you have? You have a sequence length of 512. So for each of the 512 positions, you will have a corresponding embedding, and that embedding again has to be the same size as your vocabulary embedding. So again 768. So for 512 positions, you have 768 dimensional embeddings. This is not much, 0.3 million parameters. So total 31.3 million only in the input layer, right? The embedding and the positional embedding. Then unlike the previous transformer that we had seen, where the positional embeddings were just sinusoidal initialized and they were not learned, now they initialize it and they are also learned along with the other parameters of the network, right? So you could think of this 512 cross 768 matrix as a parameter matrix, which is initialized in a certain way, but then it will get trained just as the other parameters in the network. Okay. Then we look at the attention parameters. So you have three matrices, WQ, WK, WV, right? Each of them takes a 768 dimensional input, converts it into a 64 dimensional input. So the matrix would be 768 cross 64. This is per attention head, and you have three such matrices. So 3 into 768 cross 64, and then you have 12 such heads. So I'll multiply this by 12. So this gives me 1.7 million parameters for the attention head in one layer. Okay. Then you have the linear layer, which was WO. So that just takes a 768. So after you concatenate, you have that 768 dimensional vector, then you multiply it by WO and again get a 768 dimensional vector. So that WO is going to be 768 cross 768, which is 0.6 million parameters. And for all the 12 blocks, you will have 1.7 million plus 0.6 million, which is 2.3 million multiplied by 12. So you have 27.6 million parameters for the attention block, right? The multi-head, masked multi-head self-attention block will have 27.6 million parameters summed up across all the layers. Okay. Then let's look at the feed-forward layer. So feed forward layer has, what does the feed forward layer do? Let's just see that. It takes 768, transforms to 3072, again transforms to 768. So this is going to be a 768 cross 3072 matrix. Then this is going to be a 3072 cross 768 matrix, right? That's why you have two matrices of this dimension. Okay. Then you will have 3072 biases here and 768 biases there. Okay. That's why you have this, and so this sums up to 4.7 million parameters. Yeah. So each of these guys would have a bias. So that's why you have 3072. Each of these guys will have a bias. That's why you have 768. Okay. If you do this for one block, it's 4.7 million. So you multiply by 12 blocks, you get 56.4 million parameters, right? So then you have embedding layer had 31.3 million parameters, attention layer had 27.6 million parameters, feed forward layer had 56.4 million parameters. The total number of parameters is roughly 116 million. Now I think, yeah, one thing which we did not do is that At the end, you get 768 dimensional outputs, right? That you again transform to a 40,478 dimensional output, right? Because this is the probability distribution, right? So you will again need a 768 cross 40478 matrix here, but at the input you already had that matrix, right? Correct? So these matrices can be shared. That's why I have not counted them again. Is that okay? This is called the input embedding matrix, and this is called the output embedding matrix. These could be shared, so I have not counted them again. If you count them, if you don't share them, then some parameters will get added. Okay? Okay. So the GPT-1, as I said, was like really a smallish model as compared to what modern models are, 117 million parameters. Nowadays we talk about 7 billion, 13 billion, 70 billion parameters, right? So it was very, very small as compared to that, but this was the initial model that had come out. Okay.